The secure design principle of defense in depth aims to increase security through diversity. The idea is not to rely on a single defense or even a single kind of defense. That way, if one defense is overcome, there is still another one to get past. This principle can mitigate damage from an attack or can prevent it altogether. An example application of defense in depth would be to do all of the following. Use a firewall to prevent access to all network ports other than that of the outward-facing web server. Encrypt all sensitive data, like employee records, when stored at rest, for example on the hard drive. And use a type-safe language to write the web server to prevent various classes of attack, like buffer overruns. A less diverse defense might rely on one of these, but not all of them, and then be vulnerable if the defense was bypassed.
One common application of defense in depth is to the authentication process. Now we know that passwords can be chosen poorly and possibly guessed by adversaries, thereby bypassing the intent of authentication. Passwords can also be stolen. Now, one way to defend against a stolen password is to encrypt the password database that keeps those passwords. But to do so would assume that compromise is possible. A company may think that all of their outer defenses, firewalls and secure software and fully patched systems, should keep adversaries out. But this is probably a bad assumption, and therefore an extra defense of encrypting the password database is a good idea. That's what should have happened for the RockU attack back in 2009, when RockU was compromised and their password database was stolen. All of the passwords were stored in plain text, exposing all of that information to attackers. Now, another sort of defense in depth is the use of community resources. The idea here is to depend not only on yourself, but to depend on a diversity of people toward solving the security problem. One way to do that is to use hardened code, perhaps from other projects. For example, rather than rolling your own crypto libraries, you could use libraries implemented by others and tested and assured over time. On the other hand, you shouldn't just trust them out of the box. You probably want to test that they will meet your needs and ensure that you're using them properly. Another way to use community resources is to vet designs publicly. This is typically what happens with modern crypto systems. Instead of trying to keep the algorithm that is used hidden, the designers of the algorithm make it public so others can comment on it and potentially find mistakes. Finally, stay up on recent threats and research. There is a broad security community that is tracking the state of affairs in security today. So NIST is a good place for standards. OWASP, CERT, and BugTrack have vulnerability reports. SANS NewsBytes has a great collection of the latest top threats. And of course, the latest and greatest research and long-term trends in technology can be found in academic and industry conferences and journals. Now let's look at a failure to use community resources, and that is using broken crypto implementations. So it turns out that getting crypto right is hard. Not only should you not design your own algorithms, you probably should not implement them yourself because there are many things that you could get wrong. For example, for a long time, modern implementations of RSA had a timing channel that could be exploited to steal the entire key through remote experiments. It's also the case that people have used crypto systems incorrectly, for example, not generating keys with sufficient randomness. The important thing is to use vetted implementations and algorithms and be sure that you are using them correctly.
The final design principle in our list is monitoring and traceability. This principle is an acknowledgement that there is no perfect security, and eventually all systems will succumb to an attack. As such, we need to design systems that allow us, firstly, to discover when an attack has taken place, and secondly, to figure out how the attack succeeded, so that we can try to stop it the next time. A way to satisfy both aims is to have the system log relevant information during its operation. Such logs will contain things like transactions processed, failed login attempts, and other unexpected events. The logs produced by a system can then be aggregated with other logs of systems on an enterprise's network. And together, when considered, all of these can aid the diagnosis of attacks. Software like Splunk can be used for aggregation.